Alright, here we have the very first lecture of Unit 2, which corresponds to Section 2.1 from the textbook. And it's here we introduce the Cartesian coordinate system, which is the primary coordinate system you'll not only use for the remainder of this course, but you will also use throughout the remainder of pre-calculus, Calculus 1, Calculus 2, Calculus 3, differential equations. So to say this coordinate system is important is a little bit of an understatement. Now, the Cartesian coordinate system is a two-dimensional coordinate system in which points on the coordinate plane are expressed as ordered pairs. So, the first number in the ordered pair is the x-coordinate, the second number is the y-coordinate. So, if I label this point right here, this will be at coordinate 1, 2, where the first number represents x position, the second number represents vertical positioning, or what we call the y-coordinate. Now, if I look at this point in the two-dimensional space, or this point in the plane, this is at 2, 1. Note that 1, 2 and 2, 1 are two different positions in the plane. That's why we call ordered pairs, well, ordered. This point is at x value 4 and y value 0, so that's 4, 0. We'll just label a couple of these. This point here is at, say, -1, 3. This point is at -2, -1. So you always look at the x position first. This point is at 0, -3. And this point is at 3, -1. And you get the idea. So you can see how we can describe a point in space using this style of coordinate system. Now, as you can see, the Cartesian coordinate system is basically constructed by taking two number lines and having them intersect at a 90-degree angle at each other's 0. So that will partition the plane into 4 quadrants. This is quadrant 1 right here. This is where every coordinate is positive. Then we've got quadrant 2 where x values are negative, y values are positive. Quadrant 3 is where everything is negative. Quadrant 4 is where x is positive and y is negative. So now that we have the coordinate system down, let's go ahead and derive a few formulas. So suppose I want to determine the distance between 2 points. And I want to do this without using a ruler. So knowing only the coordinates, is it possible to figure out the distance? And the answer is yes. So our goal is to figure out, hey, how far are these points from each other? And I'm calling them x1 and y1 and x2 and y2, because if I can figure out the distance between two arbitrary points, then I'll have a formula that works for any 2 points. So if we look at this first point, this is at x coordinate x1, y coordinate y1. The second point is at x coordinate x2, y coordinate y2. So you can see where it lines up with the x and y axis. And the trick to coming up with the distance formula is by applying Pythagorean's theorem, which we used in the first exam. So what we're going to do is we're going to go ahead and apply Pythagorean's theorem. So we know that when we're looking at distance along a horizontal line segment or a vertical line segment, that's one-dimensional in nature. For example, to figure out the distance from here to here, I only need to look at the x-coordinates. The y-coordinates don't matter because the y-coordinates between those 2 points don't change. So the distance between there and there is x2 minus x1. And this distance here is just the distance between the two y-coordinates. So that's going to be the higher y value minus the lower y value, which is y2 minus y1. So we just apply Pythagorean's theorem, which states leg squared plus leg squared equals hypotenuse squared. So it's essentially stating x squared minus x1 quantity squared plus y2 minus y1 quantity squared equals distance squared. And then if we want to get d by itself, we just square root both sides. So take the square root of both sides. Now you might be wondering, Mr. Roberts, don't you need a plus or minus? If you take the square root on both sides, you're supposed to have a plus or minus. And algebraically speaking, you are correct, but in the context of what we're doing, this represents distance. Distance is always positive, thus we do not need the plus or minus here. And there's our distance formula. So the distance between any 2 points is going to be the difference of their x-coordinates squared plus the difference of the y-coordinates squared, and then take the square root of that sum. And there's our distance formula. Let's go ahead and derive the midpoint formula. So the idea with the midpoint formula is I want to figure out the coordinates between the, well, middle point. So we got this first point, which is at x1, y1. This point is at x2, y2, and I want to find the point in the middle. Now it is a point, thus it can be described with an ordered pair. So what I need to do here is figure out the x-coordinate and the y-coordinate. So let's start with the x-coordinate. So the x-coordinate of this point is this x value, which you notice is going to be directly in the middle of x1 and x2. And if you recall, going back to just fundamental arithmetic, to find the middle number, you take the average. So to take the average, you add and divide. So there's the coordinates of the x-coordinates of the midpoint. And right here is where we have the y-coordinates, and notice it's right in between y2 and y1. To figure out the number that's halfway between y2 and y1, you take the average. So that's our midpoint formula. So our midpoint formula essentially states the middle point is the average of the x's and the average of the y's. Cool. Alright. And let's just do a quick example while we're here. Let's make up a quick example. Let's compute, let's say, distance and midpoint between, let me make up 2 coordinates. Let's say -1, 5, and 3, -11. So let's go ahead and do the distance first. So what a lot of people like to do is they like to label it. They'll label the first point, so there's my x1 and y1. The second point, here's my x2, y2, and then it's a straightforward application of the formula. So then the distance is going to be the difference in the x's, so that's 3 minus -1 squared, plus difference in the y, so y2 minus y1 squared, so that's -11 minus 5 quantity squared. And when you simplify that, you get the distance between those points. So that's 16 plus 16 squared, which is 272. 272 divided by 16. So that will reduce down to 4 root 17 is the answer you get there. And then the midpoint is going to be the average of the two. So if I average the two x's, so add up and divide, I would get 1. And then if I average the y's, 5 plus -11 divided by 2 gets me -3. And that would be the point directly in between the two. Alright, cool beans. So that's distance and midpoint, which brings us to graphs of equations, something we'll be studying throughout the remainder of the course. The graph of an equation is the set of all points that satisfy the equation. So it's basically all the ordered pairs that make the equation a true statement. So if we look at this first example, it's asking, hey, is this point at -1, 4 on the graph of y equals x squared plus 3? Well, we'll plug it in and see if it's true. So we just want to make sure we don't get our x's and y's mixed up. So if I set the y value to 4 and the x value to -1, you get a true statement. So the answer is yes. Now let's look at this next example. So there's our x coordinate, there's our y coordinate. So if we set the y coordinate to 5 and the x-coordinate to 0, we get 5 equals 3, which is false, so no, that point is not on that graph. Now, do be wary, almost all the graphs we're going to study have an infinite number of points on them. So just be wary that just because a graph has an infinite number of points, that doesn't mean every point will satisfy it. Now, when we're studying graphs, there are two key points, or two types of points that are crucial to studying a function. Those are what we call intercepts. And there's two types of intercepts. There's the x-intercept of a graph. So the x-intercept of a graph is wherever a graph touches the x-axis. Now, if you were to look at the Cartesian plane, you would notice that any point on the x-axis, 2, 0, negative 1, 0, 3, 0, 5, 0, 100, 0, they all have something in common in that they all have a y value of 0. So in order to be on the x-axis, the point has to have a y-coordinate of 0. If the y-coordinate is positive, then it's above the x-axis. If the y-coordinate were negative, then it'd be below. So that means to solve for an intercept algebraically, we set y to 0 and solve for x. The y-intercept is on the y-axis, which means the x-coordinate is 0. So set x to 0 and solve for y. So x-intercepts and y-intercepts are separate. The only point in existence that is both an x-intercept and a y-intercept is what we call the origin, which is at coordinates 0, 0. So when it says determine intercepts, I want x-intercepts and y-intercepts, and those are separate. So we're going to treat those as separate problems. So if I want the x-intercept, I'm going to set the y-coordinate to 0 and solve for x. So set y to 0 and solve for x. So x-intercepts, you're solving for x values. So we got a quadratic equation. We did a bunch of these on the first exam. And you get x equals negative 2, negative 1. So we have two x-intercepts, negative 2, comma 0, and negative 1, comma 0. Notice that the y value is 0. That's what makes it an x-intercept. And then for the y-intercept, we set the x-coordinate to 0. So this will just about solve itself. You get y equals 2. So then we have a y-intercept at 0, comma 2. And again, we're being careful to not mix up our x and y values. So let's look at one more example, and then we'll move on to circles. So let's figure out the x and y intercepts of this absolute value graph. So for x coordinates, we set the y to 0 and solve. So we did a handful of these on the first test. So you want to isolate the absolute value. So the distance of the expression x minus 3 from 0 is 5. So it's 5 units from 0. So that expression could be 5 to the left, or it could be 5 to the right. And there we have our solution. So we get x-intercepts at 2, comma 0. Yep, 2, comma 0. And another one at negative 2, comma 0. That's where the error was. I knew something wasn't right. So, and then the next one we get is at 8, comma 0. So there's our x-intercepts. For the y-intercept, we set the x value to 0. And we get y equals, see here, 3 minus 5, which is negative 2. So our y-intercept is at 0, comma negative 2. All right, so there is our intercept example. So let's talk about circles. So I think we all know what a circle is, but the algebraic equation of a circle is written there, and it's of the form where x and y are your variables, so they represent all the infinite points that are on the circle. H and k are constants that represent the center. Now the center is constant in any circle. The moment you change the center, you've changed the circle. And then also radius is constant in a circle. Every point is equidistant from the center. That distance is called radius, and that is the defining characteristic of a circle, is that every point is equidistant from some center point. So just be wary here when you're looking at this formula. Notice that the h and k, it's minus h minus k, so the coordinates for the center are the opposite of what you see. And if you look here, it's not the radius, it's the radius squared. So if we look at this example where we want to graph it, we see minus 2 plus 1, which means our center is at 2, negative 1. So the coordinates for the center are the opposite of what the equation is displaying. That's because of the subtraction in the formula. It's pre-baked into the formula. So if you need to pause right now and make a note, I highly recommend you do that. So feel free to pause if need be and make a note. The radius is going to be 3. It's not 9 and it's not 81. If you look back to the formula, you can see it's radius squared. Thus, you got to ask yourself, well, what squared gives us 9? That would be 3. 3 squared gives us 9, therefore the radius is 3. So when you're looking at the formula, this is not the radius, that is the radius squared. That's why the radius is 3. So we can go ahead and mark our center. It's at 2, negative 1. So there's our center. And then the radius is 3. So every point on the circle is going to be 3 units from the center. So what I like to do is just go in the cardinal direction. So from the center, I'll go up 3 units to get 1 point. 1, 2, 3. I'll go to the right 3 units. 1, 2, 3. I will go down 3 units, 1, 2, 3, and I'll go to the left 3 units from the center, 1, 2, 3. So, and then there's my circle. And if your circle looks a little bit like a potato, that's okay. Depends on how good you are at spacing out your tick marks. Now let's try the reverse. Instead of going from the equation to the graph, let's go from the graph to the equation. So what we need to do first is figure out our center and radius. So the center is at negative 1, 3. So we get that just from studying the graph, and the radius is 2. Notice every point on the circle is 2 units away from the center. 1, 2. Alright, cool. So if we look at our formula, we got x minus h quantity squared plus y minus k quantity squared equals radius squared. Well, there's our h and k and r, so we just got to plug those into the formula. Now x and y are variables, so they'll stay as variables, but h we now know is negative 1, which we punch on in. We know k is 3, and we know r is 2 squared. So when we simplify, that minus negative becomes positive, and 2 squared is, of course, 4. So hopefully that shows you why the coordinates for the center are the opposite of what you see. When you subtract it, it's going to make it the opposite sign. Alright. So basically our strategy when we're trying to write the equation of a circle, we need to figure out 2 things. We need to figure out the center, and we need to figure out the radius. So that's our strategies. Figure out the center and radius. Well, the center is provided, so we got that. And the radius is going to be half of the diameter. Well, half of the diameter, in this case, would be 15. Once you know the center and once you know the radius, all the hard work's done. You just got to use your circle formula, which is x minus h quantity squared plus y minus k quantity squared equals radius squared, where h and k are the center, r is the radius. So we know that the center is at 11, negative 17, and then the radius is 15. So when I simplify, I get x minus 11 quantity squared. So minus negative becomes positive, so that's why there's a plus 17 there, quantity squared. And then 15 squared is going to be 225. And there's the equation. Now, a word of warning, some of you might check your answer by trying to plug in the center. Remember, the center technically isn't a point on the circle, right? It's in the middle of the circle. So since it's not on the circle, it won't satisfy the equation. Actually, if you punch in the 0, you're just going to zero out the left-hand side. So let's look at one more example that's a bit more complicated. But our strategy is the same. So even though this is a bit more complex, we're still using the same strategy of center and radius. So center is always priority uno. So we're always going to do the center first. So if I were to do a quick sketch of this circle, it says endpoints of the diameter are given. So endpoints of the diameter just means the 2 points are on opposite ends of the circle. Well, that tells us our center is the midpoint of those 2 points. And that should sound familiar to you because just, not even 10 minutes ago we did the midpoint formula. So you're going to use the midpoint formula. So the midpoint formula is the average of the x's and the average of the y's. So that will get us a midpoint of 3, comma. So 8 minus 6 is 2. 2 divided by 2 is 1. So there's the center of our circle there. And then we need the radius. So radius is distance from the center to any point on the circle. So this is where we need to be very careful. This is where I normally see mistakes on these problems, is people confusing diameter with radius. So when I want to figure out radius, I can either compute diameter and divide by 2, or I can just be a little more direct and just compute the radius itself. I have to be wary that I'm going to have to use my distance formula using the center point. So that's why we do the center first. So we apply the distance formula, and I'm just going to go from the center to, which is 3, 1. So that's the center, which is 3, 1. We figured that out a few moments ago. To any other point on the circle, I'll just go the first one at 1, 8. So that's x2 minus x1, so 1 minus 3, quantity squared, plus 8 minus 1, quantity squared. So that's just the, difference in the x's squared and the differences in the y's squared, which is going to get you 4 plus 49, which is square root of 53. So there we have our center, there we have our radius, so we can write the equation of the circle. So that's x minus h quantity squared plus y minus k quantity squared equals radius squared. Punching in what we know h is 3, we know k is 1 because those are coordinates of the center, and the radius is square root of 53. Well, the square root of 53 squared is just 53, and there's our equation. Alright, that's a wrap on circles. So last topic in this section, let's talk about symmetry. We're going to be looking at 3 different types of symmetry. Symmetry with respect to the x-axis, symmetry with respect to the y-axis, symmetry with respect to the origin. So let's go ahead and get started. So symmetry is quite visual, and here's an example of a graph that is symmetric to the x-axis. So we know it's symmetric to the x-axis because the x-axis not only cuts the graph in half, but each half is a mirror image of the other half. So in other words, if you were to fold up this piece of paper along the x-axis, the 2 halves would line up. So that is symmetry with respect to the x-axis. It means one half of the graph is a reflection of the other. In other words, when I reflect over the x-axis, I get more points off the graph. So if I reflect this point over the x-axis, I get another point, so on and so forth. So that's how we can determine symmetry with respect to the x-axis visually. We can also do it algebraically by reflecting. So how do we reflect algebraically? Well, if something's symmetric to the x-axis, that means we can reflect it over the x-axis and it doesn't matter. If you look at the picture, we can reflect that over the x-axis and we get the same exact image. So that's what we're going to do algebraically, is reflect over the x-axis. So if I'm reflecting over the x-axis, the x-coordinates don't change, but the y-coordinates become opposites. So that's how you do it algebraically, is you switch the y variable to negative y. Then ask yourself, is equation the same? So if you change y to negative y and end up with the same equation, then it is symmetric to the x-axis. If you change y to negative y and get a different equation, then it is not symmetrical. And it's the same idea with symmetry with respect to the y-axis. The only difference is when we reflect over the y-axis, we switch the x-coordinates. So that's the way of determining symmetry algebraically for x-axis and y-axis. Now, when it comes to origin, the origin is we do two reflections. So there's an example of a graph that's symmetric to the origin, and we basically do both. Switch x to negative x, so that reflects over the y-axis, and then we switch y to negative y, that will reflect over the x-axis, and then ask yourself, is equation the same? So let's do some examples here. So when it says test for symmetry, I want you to test for all three. So you got x-axis, y-axis, and origin. We're going to test all three of these. So let's start with x-axis. So if we reflect over the x-axis, we're going to change the y-coordinate. So when we switch it, you can see here that we get a different equation. If I go to reflect over the y-axis, that means we change the x value. So instead of having x cubed, it's negative x cubed, which is, well, negative x cubed. So that's different. And then if we do the origin, that's where we do both. Switch y to negative y, x to negative x. Turns out we get a match. Because if I divide both sides by negative, I can get back to the original equation. So you can actually see that this is symmetric to the origin. Where it's not symmetric to the x-axis, you can do whatever you want to that equation, it'll never match the original. Same thing if I reflect over the y-axis. I can switch the x to the negative. You can do any manipulations you want to the corresponding statement. You will never get something that's identical to the original. But if I do both, if I switch the x and the y, you can get a match. Now let's try it with example number 2. So we got symmetry with respect to x-axis, y-axis, and origin. So x-axis means we change the y. So you can see here that this is a different equation. Now what if I divide both sides by negative? Okay, well then I get negative x squared minus 5. It's still different. You can never get a match, so it's not going to be the same. Y-axis means I change the x coordinate. So instead of having x squared, it's going to be negative x squared. And you can see here, when I square a negative, it changes it to a positive, and we get a match. So this one is symmetric to the y-axis. Let's see if it's symmetric to the origin. So you switch both. And what you end up getting is negative y equals x squared plus 5. So no. So number 1 is symmetric to the origin. And number 2 is symmetric to the y-axis. And that's a wrap. So there we have it. There's our very first lecture down for Unit 2. I'll try to get your test grades back as soon as possible if you haven't seen them already. But keep up the hard work and shoot me an email if you have any questions.